So now it's time to start our session. The first speaker is Professor Suzuki from Nagoya Institute University. The title of his talk is Derivation of Ion Equation. So please.
Thank you for nice introduction. Today I want to talk about my result entitled Derivation of the Ions Equation. First of all, I would like to thank organizers for giving me this opportunity to talk in this very nice virtual workshop. Yes, and so this result is obtained through joint work with Professor Grunier and Professor Guo and Professor Posada. So let me start from some physical background of this problem. So let me explain what is plasma. So plasma is a kind of a gas which consists of electrons and positive ions. So similarly as the usual fluid, we want to know to know the motion of plasma, we want to know the density and velocity of electrons and positive ions. The main difference between the usual fluid is that electrons and positive ions have some electric charge. As you know, electrons has a negative charge, and positive ions, of course, has a positive charge. So those electric charges making electric field, and that electric field giving some influence to the motion of the plasma. So we also need to consider electric field. So next, I talking about the main model describing plasma. So as usual fluid, we consider the equations of continuity and motions for electrons and positive ions. So we consider two fluid model. And as I said, we need to consider electric field. So we need to consider electric field. So we also need to consider Poisson equation. More precisely, electric field is given by the gradient of phi. Phi is electrostatic potential. This phi satisfies Poisson equation. Of course, it is more better to consider to take into the account magnetic field. In the case, we need to consider Maxwell equation instead of Poisson equation. But that model is too much complicated. Today, I want to consider the Poisson equation. So still, this system has 5 equations. So still a little bit complicated. So physicists often use a simpler model. So let me explain how to simplify this model. So the one of the typical way to of the simplification is that they assume that Boltzmann relation, namely electron density is given by the function of potential electrostatic potential phi in this way. In the case, we don't need to consider the equation of the continuity and motions for electrons. And thus, we have the following ion equation, this equation. The first equation is continuity, or the equation of continuity. And the second equation is motion equation. And we also need to consider Poisson equation. Here we use Boltzmann relation. Usually we have to consider this part for electron densities. So we replace electron densities by using this relation. So it is a closed system for 3 unknown functions. So rho u phi. So the main purpose of this talk is to derive this ions equation rigorously from 2 fluid model from electrons and positive ions. So let us formulate a mathematical program. 2 fluid model is given by the following system. As I said, it has 5 equations. In this system, t means time variable and x means space variable. N means electron density, V means electron velocity, rho means ion density, and U means ion velocity, and phi is electrostatic potential. Those 5 quantities are unknown functions which we are looking for. The first equation is the equation of the continuity of the electrons. And the second equation is a motion equation. So here, anyway, sorry, this equation is, in this equation, we already use suitable scaling. Sorry, I forget to mention it. And this epsilon is the ratio of electrons and positive ions. And this number is quite small. It's 10 powered to -3. So it's really small number. And this parameter is a very important parameter in this talk. And next, I'm talking about this term. So this term comes from the pressure of the electrons. So here we assume that the pressure given by this way. So we consider isothermal flow. So to derive Boltzmann relation, we need to assume pressure is given by this isothermal flow. And this T is of course, it's constant. It is a ratio of the temperature of electrons and positive ions. And usually this number is greater than 1. But precisely, it's really big number. So the last term comes from the Coulomb's force, which influences the motion of the plasma. And the third equation is a continuous equation of ions, and the third equation is motion equation. And here H is enthalpy of the positive ions. The definition is like this. So this notation are often used for usual fluid dynamics. So I just borrow the same notation. And the last equation is a Poisson equation. So next, I would like to put the initial data for this 2 fluid model. So we express initial data with index 0 as usual. And it is assumed that these initial data converges to the constant state as x tends to infinity. I mean that, yes, sorry. So this n bar and rho bar are constant. And we also assume that strictly positivity of the densities like this. So of course, n bar and rho bar also positive constant. So we do not discuss vacuum. And to solve Poisson equation uniquely, we need to put a referential point of the potential phi. we take differential point at the infinite distance. So namely, we construct the solution of which electrostatic potential converges to 0 as x tends to infinity. To construct the classical solution to the Poisson equation, the following condition is necessary. So let me explain, derive this condition. It's so easy to derive. So we know that the phi goes to 0 at infinity, at the infinite distance. In the case, if we look at the Poisson equation, so this term, I mean, the Laplacian phi also go to 0. So at the infinite distance, so rho and n should be equal. So this constant is that variable. So we need to assume this equality. And it is assumed to be satisfied the following condition. Enthalpy is an increasing function. So this is a very usual assumption in the fluid dynamics. So we use this assumption. So I do not want to my talk complicated. So just for simplicity, we assume n bar, rho bar, and t is equal to 0 in this talk. Of course, we can discuss general constants, but just for simplicity, we want to assume this condition. So next, I would like to talk about zero mass limit. Zero mass limit is the limit as epsilon tends to 0. Then we can derive Ion's equation. As I said, so this epsilon is a very important parameter in this talk. And only the second equation, this parameter appear. So let us discuss this zero mass limit formally first. So simply we put epsilon is equal to 0 in the two fluid model. Then we have the this model, this system. So except second equation does not change. So look at the two fluid model. So we set epsilon is equal to 0. So this term is vanished, and we assume that t is equal to 1. So we can get this equation. Other equation does not change anything. Then we notice that, so from this equation, we can get Boltzmann relation. So let me explain more detail. So so we take differential point of electrostatic potential at the infinite distance. So at the infinity, phi goes to 0, and n also go to n bar. It's go to n bar, and we assume that this is 1. So at the infinity, the inside of the gradient is equal to 0. So we see that we can erase this gradient. Then we taking exponential function, we can get Boltzmann relation. So using this Boltzmann relation and denoting the limit variable with index 0, we can get the following Ion's equation. So let me explain more detail. The third equation is I just write down with this new notation. And the fourth equation also just write down like this. And the last equation, we get Boltzmann relation. So we substitute this relation in here, then we can get this equation. So of course, this system is a closed system for 3 unknown functions, rho, u, phi. For the time global solvability of this system is well studied. So for example, Professor Guo and Posada consider this system in the whole space, and they showed time global solvability. And Professor Nishibata, Onawa, and me consider the time global solvability in the half space. So anyway, so we can get the time global solution of this model. So it is yes, the solvability is not the issue. So next, I would like to discuss about the quantities of electrons. So we already know that electron density obey Boltzmann relation in this way. So next, I want to consider electron velocity, V sub 0. So V sub 0 is a limiting variable of the velocity of the two-field model. So we easily can see that V sub 0 solves the following equation. Let me explain more detail. The first one, it just comes from this one. So we just replace E by 0. It's just a new notation. So we can get this, the first equation. So let us consider the second equation. Second equation comes from the second equation of the two-field model. So if we take curl of the, if we take a curl of this equation, in the case we have a gradient here. So the third term and the fourth term vanish. We have only this part, and we divide epsilon squared, then we can get this equation. And it can be solved by the same way as in incompressible Euler equation for this system. So indeed, just for simplicity, we assume that initial velocity satisfies irrotational. The curl V0 is equal to 0 at the initial time. In that case, the velocity can be written by potential flow as usual. So if the velocity is given by the potential flow, so in the case, the potential flow always satisfies the second equation. Then we substitute this one to V sub 0. The equation is this equation. And we see that if n sub 0 is really close to 1, it's just like a Poisson equation. So I would like to say that this equation is an elliptic equation, and n0, these n0 already given, so it is not so difficult to solve it. So in this way, we can get we can get the solution of the limiting equations. Sorry, I say that. So I would like to say that these three equations and these two equations I would like to call a limiting equation. So anyway, we can obtain the solution of the limiting equation as above. And we also can assume that those solutions have the following regularity. So this regularity a little bit, it looks a little bit too much, but it is not main topics of this talk. So I would like to assume enough regularity in this way. So let me summarize our question. The first question is the limit of the quantities of positive ions. So I would like to consider that the ions variable converges to the solution of the limiting equation or not. The second question is the variables of the electrons converge to the solution of the limiting problem as epsilon tends to 0. So here is a remark. The first question is enough to derive the ions equation. So since these three quantities satisfies this ions equation, so if we show this limit, we can derive ion equation. The second question is a little bit a mathematical question, but we have some interest to discuss this question. So I would like to consider a second question. So let us mention the main result for the question 1. So we consider asymptotic expansion with respect to epsilon. So it's very usual way to consider this kind of the limit. So I mean that the solution of the two-fluid model is given by the summation of the solution of the limiting equation plus the first order term of the epsilon in this way. So here I would like to emphasize that this is not type. So only velocity v sub e, we do not put epsilon here. So we see that v sub e, its velocity, so it is velocity for electrons. It is ill-prepared. So usually we call this kind of data ill-prepared. Later on, I would like to explain more detail why we call ill-prepared. But important things in here is that only velocity we do not put epsilon. This part is unusual. So from two-fluid model, we see that N1, V1, rho 1, U1, phi 1 solves the following equation. So I would like to call this equation new two-fluid model. So these first order terms satisfies this equation. So let me explain a little bit more for this equation. So we can find, the term having epsilon is highlighted by blue in this way. So as you know, so we now consider epsilon tend to 0. So these terms are not so difficult to handle. It's very mild terms. But these two terms are a little bit programmatic. Since epsilon tend to 0, it's diverge. So we need to carefully handle these terms. And we, on the right-hand side, we have some sigma term, sigma 0, from sigma 0 to sigma 3. So those are nonlinear terms. But if I write down everything, it's too much complicated. So I omit it to write detail. But those are very mild terms. They don't have any singular term like this. And we put initial data, and we express the initial data with 0, like this. So here is a remark. If we have a uniform bounds of the first order terms, first order terms with respect to epsilon, in that case, we can justify this limit. The ions quantity converts to the solution of the limiting problem. So it's very easy to see from this expansion. So if ρ1 and u1, phi1 are uniformly bounded with respect to epsilon, in the case, if we consider epsilon tend to 0, this term and this term disappear. So we can get the limiting solution. So we can justify this limit. So maybe I do not have enough time to give a proof of this limit. So I just mentioned the idea of the proof. So the main programmatic term is this one and this one. So it has a singularity. So we would like to make some cancellation of the these singularity. So these singularity, by using symmetricity of the hyperbolic equation, we can make some cancellation with this term and this term. So, but still we need some cancellation to handle electrostatic potential phi. So to get the cancellation, of course we use this Poisson equation. More precisely, we rewrite this equation like this. So we make some time revolution equation of the phi. Then we can find some cancellation with this one. So anyway, the proof lies on the making cancellation with using a very nice symmetricity of the equation. So let me explain our main result. So we can take any initial data in the Sobolev space. Of course, we need to assume that initial densities belong to this Lebesgue space. This condition is necessary to discuss since we have to solve the Poisson equation. So the right-hand side should be belong to the Lebesgue space. Otherwise, we cannot find the solution phi. I mean, I want to make a solution gradient phi belong to L2 space. So we need such a kind of regularity for densities. So this is the meaning of this assumption. So then there exists time capital T0 and such that the solution of the new two-field model exists and satisfies the following uniform bounds. Of course, this C0 and T0 are independent of epsilon. So therefore, we see that the two-hooded model can be written the summation of the solution of the limiting solution plus some term of large O epsilon. So here is a remark. So from this theorem one, this theorem one justifies a derivation of the ion equation. Namely, if we consider the limit of epsilon tend to 0, these terms, of course, vanish. Then we can get the ions equation. So, and the second remark is that it is also seen that for electron density is also can be written in this form. So, but we do not know the velocity. As I said, only velocity is written in this form. So we don't know V sub 1 converts to 0 or not. So other terms has epsilon, and the first order terms uniform bounds of epsilon. So we see convergence. So that is the second question. So I will later explain this one. And I would like to say that this result is the first result of the zero mass limit for our Euler-Poisson equation. However, there is some related result. So this limit is very similar to the low Maha limit for the compressible Euler equation. Compressible Euler equation is given by this equation, and this epsilon squared corresponding to Maha number. So the difference between our program is that we have additionally gradient phi in the motion of the motion equation. So this only the difference is this term. So the other part is very similar. And of course, if we take low Maha number limit, we can get incompressible Euler equation. So this is a very well-known limit. So this limit for well-prepared case, Professor Evin and Professor Krasnerman Maeda discussed. And ill-prepared case, Professor Ukai and Mathilde discussed. So we borrow some idea from the paper written by Mathilde to show this theorem one. So let us switch gear to the second question. Oh, sorry, I omit the proof. So let us discuss second question. The second question is a limit of the quantities of electrons. So as I said, we know that electron density can be written in this way. So we already know the convergence of the density. So it remains to show the velocity. So let me explain the difficulty of this question. We can take any initial data for two fluid model, but we cannot take the initial data of the solution of the limiting equation arbitrarily. So indeed, if we assume that the initial velocity of the so if we assume that potential flow, it can be written as, it satisfies this equation. So V sub 0 is determined by this equation. and n sub 0 is given data, so we cannot take v sub 0 arbitrarily. So generally speaking, so the initial data of the two-phase model and the initial data of the solution of limiting equation does not match. More precisely, the initial data of the two-phase model is given by in this form. So initial data of the solution of limiting problem plus the initial data for the first term. So steep change between velocities appear near the initial time. So we must handle the initial layer to discuss question 2. That is a main difficulty to discuss question 2. Here is a remark. So we choose the density in this form. So in this case, no layer appear, since if epsilon tend to 0, this term vanish. So at the yes, so we can take almost the same data of the densities for two-phase model and the limiting model. So usually people call this kind of data well-prepared data, and people call this kind of data ill-prepared data. So that is a meaning of ill-prepared. So I would like to mention our main result. So this to discuss question 2, we need to decompose the first order term by the initial layer part and the remainder parts in this way. So n sub L, v sub L, phi sub L, it's corresponding to initial layer part. And n sub R, v sub R, phi sub R, those are remainder parts. And we define initial layer parts by solving the following equation. The left-hand side is a linear equation, linearized equation of the new two-fluid model. And the right-hand side has some nonlinear terms, pi 1, pi 2. So if I write down everything, it's a little bit complicated, so I omit it. But those terms having epsilon, so it's not programmatic. And we put initial data, this data. So the layer part have a same initial data of the new two-fluid model, and with, yes, like this. But to discuss question 2, we need to assume the initial data, the curl of the initial data is equal to 0, I mean rotational flow. So let me mention our main result. There exists time t sub L independent of epsilon, such that if the initial data sufficiently small in this weighted Sobolev space, in the case we have the following inequality. Here, K is some compact set in the whole space R3. And to handle the initial layer, we integrate t is equal to 0 to t is equal to t sub L. So yes, to handle the initial layer. Then this quantity is bounded by this one. So this is just constant. And we have a epsilon term in here. So this estimate tells us that if epsilon tend to 0, this term going to 0. I mean that if we consider epsilon tend to 0, log epsilon goes to minus infinity, and we have negative power here, and delta is an arbitrary positive constant. So this blue term going to 0. So we can get the convergence of the initial layer part, but only local norm. I mean, K is just a compact set. So the remainder part is a very nice. I mean that it's converged to 0 in this strong topology. So it's very minor term. The most programmatic part is layer part. So let me explain the main idea to show this estimate. So we use some dispersive estimate. Indeed, we can find some Klein-Gordon structure in our Euler-Poisson equation. I mean, layer equation, initial layer equation. So for simplicity, we suppose that nonlinear terms are 0 and n sub 0 is 1 in the initial layer equation. The result is this equation. Then we can find the Klein-Gordon equation. Let me do it. So we apply this differential operator to the first equation. Then we can get this one. I just apply this operator. So the first term, second derivatives with respect to t, and we have a derivative t inside of the divergence. Then we use this equation, the second equation. So using the second equation, I substitute this part, I mean the highlighted yellow, this equation. Then we have a divergence gradient. It means Laplacian. So we have this equation. And we also use the last Poisson equation. So gradient phi can be replaced n like this. So this is Klein-Gordon equation. We also can find some Klein-Gordon equation for velocity and phi. Yes, I omitted the detail for the Klein-Gordon equation, v and phi. The next, I would like to consider the limit. What does this limit mean? So let us using change of the variable, s is equal to t over epsilon. In the case, we have exactly same Klein-Gordon equation. And we notice that, so the limit epsilon tend to 0 is equivalent to s tend to infinity from this change of the variable. So to know the limit of the epsilon, it's enough to know the time-long behavior of the Klein-Gordon equation. So so there's a lot of method to discuss time-local behavior of the solution of the Klein-Gordon equation, but we use local energy decay estimate, more precisely local energy decay estimate invented by Professor Moravens. So the proof is a little bit complicated. I could not explain in 5 minutes. So sorry, I skipped the proof, but the main idea is using this dispersive estimate, which comes from Klein-Gordon structure. So finally, I would like to mention some concluding remarks. For the first question, which is a limit of the quantities of positive ions. So for this question, we see that the two-field model, the solution of the two-field model can be written the summation of the solution of the limiting solution plus some term large O epsilon in this way. So we easily see that this limit as epsilon tend to 0. For the second question is a limit of electrons variable. So density n is also can be written as the same as question 1. So it does not matter. The difficult part is the velocity. So velocity we have to divide in 3 parts. So limiting solution and the initial layer, the solution of the initial layer, and some remainder part. Remainder part is very nice. It's converted to 0 in the very strong topology, but the layer part it's decaying, but only local norm. So this is our main result. And let me introduce some open problems. The first question is it's a mathematical question. So what happens on the torus? As I said, to consider the question 2, we use dispersive estimate. So if we consider torus over the torus, we cannot use such a kind of estimate. So it is a mathematically difficult question. The second question is a more physical question. So as I said, more relevant model is Euler-Maxwell equation. So it is really good question. What happens for the Euler-Maxwell model? So I think that my time is almost over. I stop my talk here. Thank you so much for your kind attention.
Thank you for your interesting talk. Are there any questions or comments? So Professor Terasawa, please.
So thank you for a nice talk. And so I'd like to ask a question about the somehow negative results. So you said in the question 2, and the first convergence of VL,
yes,
you said you have to integrate in time.
Yes.
But is it really necessary thing to reduce to 0?
Yes, in some sense, of course, we need to integrate from 0 to some t sub l. But more good result is that there is a possibility we can show that VL goes to 0 in strong topology, but it's not start from 0 like eta TL.
Okay.
Some space, the eta is 0, greater than 0. So this decay is more good estimate. And there is a possibility we can get this estimate.
Okay. So if you take eta equals 0, you can prove it's not possible, right?
Not possible. Not possible. The main reason is that those initial data does not match
Okay.
at the initial time, so it's impossible.
Okay. Thank you very much.
Thank you so much.
So thank you.
Are there any comments or questions? If not the case, sorry. Dr. Sakamoto, please.
Yes, thank you very much for your talk. And I wish to know what will be a difficulty if we consider the problem with the Euler-Maxwell equations.
Oh, the difficulty is, of course, to handle the magnetic field.
Yes.
But it's a little bit explained. A little bit difficult to explain the difficulty. But I would like to say that given magnetic field, so I just consider some Euler-Poisson equation, and we additionally adding some the fixed magnetic field. Even such a case, I could not show it.
Oh.
So I think that the Euler-Maxwell equation is much difficult.
Yeah, because the magnetic field depends on time, right?
Yes, exactly. Yes.
Thank you very much.
Thank you very much. So let's thank the speaker again.